basically on electrons there will be electrostatic attractions because the two guys are oppositely charges. Electrostatic attraction will be felt by the new electrons, that is F1, and then as electrons are doing kind of a circular motion here, it will feel the centrifugal force which is outward from the nucleus, right? So those two forces will be cancel off each other, and so that new electron is able to do its circular motion continuously. That was the idea. So that electron is not going to fill to the nucleus, right? To keep the distance from the nucleus constant, that means to keep this value a constant, to keep this value a constant, to keep the distance from the nucleus constant, right? You have to travel in a constant velocity. You have to travel in a constant velocity. From this model, you came across the 288 electronic configuration. With the first orbit, only 2 electrons can appear with these 8 electrons and this with 8 electrons. So that is how the 288 configuration formed according to this model, right? Waves won't have a definite position. Won't have a definite position. So that electron can't occupy a definite position from the nucleus. It can't have a constant distance from the nucleus. This is the pitch of the hydrogen atom. You don't have million electrons here. You just have only one electron. At one frame it is here, at the other frame it is here, at the other frame it is here, next one here, here. If you are to put all the million frames on top of the other, you will get this picture. This is so hydrogen atom. Love is like the wind. You can feel it, but you can't touch it. Right? Like this, our electron is like the wind. I can feel it, the existence, I can feel it, but I can't touch it. The quantum number set is kind of a barcode of your electron. If you have a better barcode reader, if you have a good reader, barcode reader, you can gather all the information of your electron by just scanning that barcode. Right, good evening, Lavai. Let's start the class, right?
Good evening, sir.
Good evening. You can hear me now, right?
Yes.
No worries with the sounds, no?
Yes.
Right, okay, thank you. Thank you, Chris, right? Okay, let's start the class, right, for the today's session. Right, last day we have discussed about what? Yes, we had done the hydrogen spectrum, right? We have discussed all the theories and all the things, all the points we should know about the hydrogen spectrum, right? So now we are going to discuss about the Bose atomic model, right? Bose atomic model, right? Actually, before going to the Bose model, let's have a quick recap of what we have learned up to now, the atomic models we have studied up to now. Let's have a quick recap, then after that we can go for the Bose model, right? Okay, so here I have mentioned the models we have studied so far. All started with the Dalton, right? All started with the Dalton with its golf ball model, right? Then comes the Thomson's plum pudding model after he found the existence of electrons, the negative charges on atoms, right? Of atoms. So after that he has introduced the plum pudding model of the atom, right? So it looks like this, right? So basically what happens from coming from Dalton to Thomson was actually the charges were introduced. Basically the electrons are introduced to your atom by the Thomson's model, right? The plum pudding model, right? After that Rutherford tried to actually confirm this model practically, experimentally. So he had done the gold foil experiment, Rutherford's gold foil experiment, to prove this model, but the idea was a different idea, right? With the observations and conclusions, Rutherford came up with his nuclear model. So they are first they have introduced the atomic nucleus. Actually, what happened coming from the Thomson's model to the Rutherford model was actually in Thomson's model, he had a very hard sphere. With Thomson's model, had a hard sphere, right, carrying the positive charge, which neutralized the negative charges of your atom, right? The positive charge was carried by a hard sphere, basically the golf ball kind of a hard sphere, right, in the Thomson's model. But when it comes to Rutherford model, the difference is basically Rutherford said not all the mass of the atom is not like this spread throughout the atom, but he said, instead of that, he said all the mass, the total mass of the atom is concentrated to the center of the atom. All the mass of the atom is concentrated to the center of the atom, which is known as the nucleus. He introduced the nucleus to the atom, so it is referred to as ultimately the nuclear model, right? That was the nuclear model of the atom proposed by Rutherford in 1911, right? So when it comes to nuclear model, there were two failures. Right? One failure was actually Rutherford was unable to explain the origins of the hydrogen spectrum. Rutherford was unable to explain the origin of the hydrogen spectrum. And the second failure was like this: the atom is going to be kind of an unstable structure. Atom is carrying kind of an unstable structure because with some space between the nucleus and the electrons, right? So electrons can't stand like this because those are oppositely charged particles, so that the electrons will ultimately attract to the nucleus and combine with the nucleus, right? So that this is kind of a unstable structure. That was the second failure with the nuclear model of the Rutherford, right? So then the scientists were thinking of a new model to come up with to answer the two failures of the Rutherford model, right? So Niels Bohr is the scientist who proposed a good model, some acceptable model to answer those two questions, right? So what were the two questions? First question was kind of this model unable to explain the origins of the hydrogen spectrum, right? For that, Niels Bohr proposed the good idea. Last day we have discussed about that idea. So that was actually by proposing the energy level concept to the atom. So he said that electrons reside or occupy the energy levels, right? With that idea, he was able to explain the origins of the hydrogen spectrum. He was able to giving a good solution for the that problem, right? The hydrogen spectrum, right? So problem with the nuclear model of the Rutherford, right? So for the second question, the atom was unstable like this, right? For that thing also, Niels Bohr was able to give a good explanation, and Niels Bohr was able to come up with a good, good answer for that question as well. How the electrons reside, how the electrons occupy in the atom by not attracting to the nucleus. That thing also answered by Niels Bohr, right? We are going to today discuss about that model, the Niels Bohr's planetary model is also known as planetary model. Let's discuss about that thing right now, right? So yes, as name suggests, it is the planetary model, right? Niels Bohr's planetary model. You can here see the name, right? Basically, this was proposed in 1930, right? 1913, right? Okay, Niels Bohr's planetary model. Yeah, planetary model. So Niels Bohr said, look, you can see the planets revolving around the sun. The sun is our major mass of the of our solar system, and the little masses, the planets, revolving around the sun. Like that, Niels Bohr proposed that our atom also contains such kind of a structure, right? Our huge mass, the nucleus, is at the center of the atom, and Niels Bohr said our little masses, negligible masses, the electrons, will revolve around the greater mass nucleus, right? That was the simple idea of the planetary model. Let's go to the go through our note, right, and let's see what they are proposing, right? Afterwards, right, we'll discuss more about that model, right? See, this is page number 23. You can see, right, Bohr's planetary model, right? It says in 1930, Niels Bohr suggested that the atomic nucleus was surrounded by electrons moving in orbits. like planets around the sun, right? Okay, that was the simple idea, right? See, let's discuss about the model, the Niels Bohr model. It is like this. He said, okay, you have the nucleus here. This is your nucleus. This is your nucleus, right? So he said that electrons are not going to attract. Electrons are not going to attract towards nucleus because those are not like that. Those are not like this standing still, right? But instead of that, they will orbit. They will orbit around the nucleus like this. The electrons are to orbit around the nucleus like this, like planets revolving around the sun. Our electrons are also orbit around the nucleus. That was the simple idea. You have the electrons like this appearing here and there, right? So electrons are there, right? Going here and there, right? So those are orbiting around the greater mass, means the nucleus. This is the idea of Niels Bohr, right? Let's discuss how this model was able to give a good solution for the problem of electron combining with the nucleus. That was a kind of a major problem with the Rutherford model, no? As the electrons are nuclear charge compared to the nucleus. The electrons are nuclear charge, nucleus is positively charged, so that those two things should be attract according to the nuclear model of the Rutherford. But Niels Bohr said, okay, yes, that attraction is appearing, no worries, yes, this attraction will be appearing as the electrons are nuclear charged particles. Attractions will appearing, right? Nuclear attractions, yeah, we can see it as F1. Those forces are appearing, but with this model, he proposed kind of a centrifugal force, kind of a centrifugal force, which is operating, right, outward from the nucleus, which will be operating outwards from the nucleus, right? Such kind of force will be appeared when you are doing a circular motion, right? That is the idea. So you will absolutely you will feel this force, right? If you have to do a circular motion, if you are doing kind of a circular motion, you would probably, right, feel this thing, right? So let's come up with this force a bit more. Think of this one. So you will feel this thing when you are going around a roundabout, or kind of when you are doing a circular motion. Maybe when you are traveling by bus, or maybe you are when you are traveling by your bike, right? You will clearly see, right, this force appearing on you, right? When you are doing your circular motion, what will happen? You will feel that there's a force actually, right, which pulls you away from the center of the circular motion, right? Kind of a force will be felt by you, right, if you are to do a circular motion, right? So when you are traveling by bus even, right, in these round roads, right, you will feel this thing, right, normally away from the center of the pathway, right, you will feel some force appearing on you, right? You may have felt that, right, when you are doing circular motions, right, when you are traveling by bus even, right? So such kind of force, that force is referred to as the centrifugal force, that appears only when you are doing a circular motion. So what Niels Bohr said was actually, right, as these electrons are doing kind of circular motions around the nucleus, right, so kind of a centrifugal force will be appeared, right, will be felt by the electrons actually, not towards the nucleus, but it is towards outwards from the nucleus. So ultimately those two forces will be cancelled off, and so that the electron is not going to fall to the nucleus. That was the idea. That is how Niels Bohr proposed this atom is kind of a stable one, not electron is not going to fall to the nucleus, right? So what is the idea? Basically on electrons there will be electrostatic attractions, because the two guys are oppositely charges. Electrostatic attraction will be felt by the new electrons, that is F1, and then as electrons are doing kind of a circular motion here, it will feel the centrifugal force which is outward from the nucleus, right? So those two forces will be cancel off each other, and so that the electron is able to do its circular motion continuously. That was the idea. So that electron is not going to fill to the nucleus, right? So like that, Niels Bohr was a good acceptable idea, right? So that he said this atom is stable if you have to follow this model, right? So that was the second solution for the problem arised with the nuclear model, right? Okay, so you can write this stuff, Lamai. You can draw the picture at the space given, right? At the space given, you can draw this picture, start drawing the stuff, right? I'll labels these things, the electron, the nucleus here, and I'll give you the definitions of these symbols as well here, right? So you can start drawing the stuff, right? Okay, so this F1 is your electrostatic force, electrostatic attraction between the opposite charged particles that will happen, and your F2 is your centrifugal force. Centrifugal force, right? So Niels Bohr said these two are actually equal. That is why the electrons are not going to fall to the nucleus, right? So I'll give you the equation of this thing as well. The centrifugal force is actually, this is the equation. Even though this is not appearing in your research book, right? Just know this thing because this is there in your physics lessons. In your physics lesson, the mechanics lesson, you may have started now the mechanics lesson, unit 2 in physics, right? So at the later sections, you will come across the circular motions. The physics lesson starts with the linear motion, ultimately ends with the circular motion, and there you will come to know about this equation. This is the force, the centrifugal force appearing on a particle which is traveling in a circular motion, which is doing a circular motion. This m is the mass of the particle, v is the velocity of your circular motion, and r is the radius. R is the radius of the circular motion, the origin to the distance actually, that is the distance between the nucleus and the electron in this sense, right? So that is the equation. So just draw these ones, right? This one, and just have those ideas as well, right? These are electrons moving in orbits, right? So with this model, right, Thomson was able to suggest the concept of orbits as well, right? With this model, Thomson was able to suggest the concept of orbits. Before this model, you won't see the appearance of orbits. So this atomic model introduced two concepts. One is the orbit concept. To the atom is introduced by the Niels Bohr's model. You won't see such kind of a thing appearing with these models, right? Orbit concept. And second thing is actually the energy level concept. We had came through that concept when we are describing the hydrogen spectrum. Actually, that description was done by the Niels Bohr, right? So those are two major concepts introduced by the Niels Bohr's planetary model: the orbit concept, then the energy level concept. So just quickly go through the stuff here. So you have the space there to draw the stuff, right? Under the second point, which says that Bohr postulated the electrons, in order to remain in orbit, the electrostatic attraction between the nucleus and the electron must be equal to the centrifugal force. Electrostatic attraction between the electron and the nucleus should be equal to the centrifugal force. Those two things should be equal. Right? That is what is meant by the second point, right? So you can draw this picture at the space given. Right now? Right, so I'll send you a picture, right? Yeah, screen capture if you need some more time, I'll send it to you, right? Let's continue then, no? Okay, I'll discuss bit about this thing. Why I written this thing here, this equation, right? Because let's go to the sentence which is written inside the brackets with the second point. Let's go to that. Then then you would see that this equation is also important in this discussion, right? See, let's go to the point there with the second point. That sentence within brackets. Let's go to that. In other words, it is said. In other words, this same statement is appearing at the resource book. That is why I put it there, right? Put it here because that is appearing in the resource book. Every word in your resource book should be known, right? Every word in your resource book should be known. That is the minimum. That is the minimum you should know, right? When doing the A-levels, the minimum you should know is the resource book, right? So every word in your resource book should be known, right? So that is why I include all the important points in your resource book here, right? So this statement is also directly extracted from the resource book. Let's go to this, right? It says, within brackets, it says, in other words, the electrons have to travel in a constant speed around the nucleus, keeping the distance from the nuclear constant. That means to keep the distance from the nuclear constant, right? That is the idea. Let's see. So actually, with this equation, we are very able to, right, come up with that idea without memorizing the statement, right? You can, right, come across that idea if you know this equation, right? I'm again telling you, this is the centrifugal force acting on your mass, the electron. This is the mass of the electron. This is the velocity of the electron, the traveling speed of the electron, and this is the radius, or one can say the distance to the nucleus, right? Right. So the idea is this. It says to keep the distance from the nucleus constant. That means to keep this value a constant, to keep the distance from the nucleus constant, right? You have to travel in a constant velocity. Because the mass of electron is a constant. We know the mass, right? 9.1 into the power 31 that kilograms, right? So mass of an electron is a constant. This F2 is also a constant. That F2, because F2 is equal to F1. So kind of a attractive force is appearing on the electron. So F2 should be equal to F1. So it should be a constant. If you are feeling F1 kind of attraction, so to neutralize that attraction, the F2 appears. So it is a constant which is related to F1. If the F1 is kind of 5 joules, the F2 should be also 5 joules. It's a constant, right? So if the F2 was a greater value, electron will go away from the nucleus. If F2 was a smaller value than the F1, electron will come close to the nucleus. The radius will change, right? So anyway, to keep the radius or keep the distance from the nucleus constant, then you clearly see you have to maintain your velocity with a constant value. Right? Got the idea? Because this F2 is a constant, it is equal to the F1, right? So to keep the R constant, this V should also be a constant. If the V changes, if your velocity is high, what will be happen? The F2 will be high then F2 will be high means the electron will travel outward from the nucleus, right? If the F2 will be higher than the F1, the electron will go away from the nucleus, so the distance will change between the nucleus and the electron. If the F2 will be low, if your speed is low, what will happen? The F2 will be low, that means F2 will be lower value than the F1, so that F1 is greater, so electron will come closer to the nucleus. So distance will vary between the electron and nucleus. So to keep the distance between the electron and nucleus constant, you have to move with a constant speed. The circular motion should be done with a constant speed. That is what that statement says. So that can be clearly understood if you know this equation. That is not a new equation for people studying A levels, right? Because that is appearing in your physics lessons at the end of the unit 2, right? So that you will learn this thing at the physics, right? Okay. So again, go to the statement, and you will probably get the idea. In other words, the electrons have to travel in a constant speed, around the nucleus to keep the distance from the nucleus constant. Right now, that is the idea. Okay. Right. So this is clear. Right. Do you have any other questions, Lama, about this thing? Anyone with questions? Chris, do you have any problems appearing? No, it's clear, no? Right, okay. I think the other guys are also okay, right? So if you have any questions, just raise your hand and ask them, right? Okay, right, that's it. Let's go to the other points of the Bose model, right? So this is a Niels-Bohr model, right? You can label this one, right? Niels-Bohr planetary model, right? So Bose planetary model. Planetary model proposed by the Niels Bohr, right? So in 1930, right? Let's go to the note again. Let's see what they are saying further. Further, it says like this. Further, he added, it is said there, and you have some space there. So let's write the stuff there, and then we'll discuss about that thing. Just write the complete this one, right? Further, he added that. You can complete the stuff at that space, right? Each orbit is with. Just write, Lama. Each orbit is with its characteristic energy, and each orbit is with its characteristic energy. So these orbits are with their characteristic energies, right? And you can write in red color. And when going away from the nucleus, the characteristic energies of orbits increase. When going away from the nucleus, the characteristic energies of orbits increase. See? Right? It is like this. The idea is like this. So, Bohr said, right? So, these are the orbits, that 288 structure. In your O levels, you learned about that 288 structure. That is actually the simplified form of the Bohr's model. He said, right? These are the orbits appearing with your atom, right? You have the nucleus here, and this is the first orbit. N equals 1, the quantum number 1. This is second orbit, third orbit, the quantum numbers, right? And he said, right, each orbit is with some characteristic energy. The second orbit is with some E2, its characteristic energy. This thing is with its characteristic energy, and going away from the nucleus, he said that energies are increasing. That means than the E1, the E2 is greater. Than the E2, the E3 is greater. That was the idea, right? So this idea also was proposed by the Niels Bohr. This is the 3D picture. This is the simplified idea. From this model, you came across the 288 electronic configuration. With the first orbit, only 2 electrons can appear with these 8 electrons and this with 8 electrons. So that is how the 288 configuration formed according to this model, right? So you can have this picture as well in a little space. Just draw this one as well. This idea was also proposed by the Niels Bohr. So these are the orbits. These are the orbits, right? Orbits are there. Those are with characteristic energies, right? Just simply draw that structure as well. Right, no? Okay, that was the idea. Right, let's go to the now let's discuss about the failures of this model. Right? Let's discuss about the failures of the Bohr's model. Lamai, there were 2 failures to discuss, right? Actually there were 3 failures. 3 failures were there. We'll discuss about 2 failures, right? Because these things are not appearing in your research book, but they have been questioned. Remember that. I'm always saying you, the resource book is the minimum you should know. That is not the all you should know. It is the minimum you should know. If you are to go through the Pesuru book, if you go through the MCQs appearing there, you will see much more than the resource book, right? So, right, you should have these ideas as well in normally in Colombo School papers, Royal Vishaka papers, right? You will come across these ideas so that you should know these things, right? That is why we are teaching you this stuff, right? Okay, there were few failures with this model as well, right? The first failure is very simple, Lamai. First failure is very simple. All the guys know this thing, right? I'll tell you a story, kind of an ancient story, right? About the first failure of this model, right? After Niels Bohr proposed this model, right? And right, when he is relaxing in his garden, right, with a book or something, when he is relaxing in his garden, right, there was a man shouting, going closer to, going by his home, shouting, Tatio, that is in Sinhala, right, Tatio, or in English, let's say, shouting flat earth or flat man. Hey, flat man, right? There's a man shouting like that. Niels Bohr, right, heard that thing and asked that man, why you are saying me that flat man? Why you are saying me that flat man? Flat man? Why you are saying so? Right? Then that unknown man said, look, according to your theory, you just proposed now, the planetary model, according to your theory, don't you see that the hydrogen atom is flat? Don't you see that hydrogen atom is flat? Don't you see that? Right? That was a question asked by that unknown person from Niels Bohr. You see, the hydrogen atom, if hydrogen atom is to appear according to this theory, it should be a flat atom, no? 2D atom, no? Don't you see that? Right? So only one orbital is only one orbit is appearing with the hydrogen. The first orbit is only appearing with the normal hydrogen, ground state hydrogen. So you have a nucleus there, you have the nucleus, and one orbit is appearing. Kind of flat stuff. So kind of a flat stuff. So hydrogen atom should be a flat atom. So how on earth it could be like that? So that is a failure. We all know the atoms are 3D objects. We make the 3D world from these atoms, so that those should be 3D objects, right? Can't be flat like this, can't be 2D, can't be 2D like this. That is a one failure with the proposed model by the Niels Bohr, right? It can't be flat. Okay, right? Such a story was there, right? Some ancient story, right? Let's come to the right some theoretical stuff again, right? So that was one failure. Few other failures were also there, right? Another failure was actually this model was unable to explain the origins of spectrum appearing by multi-electronic systems. So actually that theory is on hydrogen spectrum is valid only for single electron systems. For hydrogen, helium plus, lithium 2 plus, for those species, the theories of hydrogen spectrum valid. We had concluded our discussion last day with that. All the single electron systems carrying the same pattern with the atomic spectra. So hydrogen spectrum theory can be used to explain the spectra appearing with the one electron system. But this theory fails with multi-electron systems. This theory fails with helium atom, which is 2 electrons. This theory fails with the lithium atom, which is 3 electrons. It is okay for lithium 2 plus and helium plus, which are with 1 electron each, but fails with helium atom, lithium atom, oxygen atom, nitrogen atom. When you have more than 1 electrons with your atom, this theory fails. That is the second failure. Then another failure was there. Three failures were there with this model. Let's discuss the third failure, right? After writing the first two. Right? Okay, let's go to this stuff, right? Let's write the failures. Failures of Bohr's model. Right? Let's write. Before writing the failures one by one, just write this para. Right? Like that. Right? Like this. Right? Even though Bohr's atomic model was able to explain, just write the line. Even though the Bohr's atomic model was able to explain, the theory behind the hydrogen spectrum, even though Bohr's atomic model was able to explain the theory behind the hydrogen spectrum, but it failed on following. Let's write the failures one by one. Number one. According to this theory, according to Bohr's theory, hydrogen atom is flat. Within brackets you can write 2D atom. It is 2D, two-dimensional. Hydrogen atom is flat. Within brackets 2D atom. Two-dimensional atom, right? So it can't be, right? So it's a failure. Right, number two. Number 2, right? This theory could not explain. This theory could not explain. This theory could not explain. This theory could not explain the line spectra of. The line spectra of. This theory could not explain the line spectra of atoms or ions containing more than one electron. This theory could not explain the line spectra of atoms/ions containing more than one electron. This theory explaining only the single electron systems, right? For multi-electron systems, this fails, right? That is the idea. Atoms/ions containing more than one electron. Right now, they are these theory fails, right? Okay. Let's try the third one, the third failure. That was also a great failure. Failure number 3 with the Bose model. This theory could not explain. This theory could not explain. This theory could not explain the splitting of spectral lines. The splitting of spectral lines. This theory could not explain the splitting of spectral lines. The splitting of spectral lines in magnetic field. In magnetic field. In magnetic field. Within brackets. Within brackets. Within brackets. Just write it in red color. Zeeman effect. Zeeman effect. Write it in red color. Zeeman effect. Close the brackets. Close the brackets. Come to the normal color. And in electric field. And in electric field. And in electric field. Within brackets you can write in red color again. Stark effect. Stark effect. Close the brackets. So this model was unable to explain the Zeeman and Stark effects, which are appearing when you see the hydrogen spectrum in an external magnetic or electric field. Let's discuss that idea. What is that? What is the Zeeman effect and what is the Stark effect? Right? This is the idea. So, right? Zeeman and Stark effects. Right? The idea is this. Lamai. Say this is the hydrogen spectrum. This is the hydrogen spectrum. Lyman or any kind of seeds are. Let's say this is the these are colored lines, right? These are colored lines. Let's say take the Balmer series. Take the Balmer series of hydrogen spectrum. So this is the red color line. This is the green color line. Right? Blue, violet. Some few lines are appearing like that, right? So that is the idea. Okay. So when scientists did the same experiment applying an external magnetic field or applying an external electric field, when scientists done the same experiment of observing the hydrogen spectrum in an external electric field or in an external magnetic field, they saw the spectrum like this. The same Baum series appeared like this. This red color line, the red color line splits to two lines like that. This green color line also split to few lines like this. The blue, all the lines. Were split to few lines. Like that. These are the final lines appear, right? So the red, green, blue, violet. That single red line splitted to two. Single green line with the normal hydrogen spectrum split to few more lines. Blue line, violet line as well. All the other lines in your hydrogen spectrum was splitted to few more lines. This is known as the Zeeman-Stark effects. This will appear when you have applied some magnetic field or electric field, right? When you are observing the hydrogen spectrum. This is the hydrogen spectrum in an external magnetic or electric field. The same Baum series. In magnetic field or in electric field. So Niels Bohr unable to explain this appearance of the hydrogen spectrum, the Zeeman-Stark effect. Those are the two scientists first observed those spectrums in magnetic and electric fields, right? The Zeeman and Stark. So that was the failure, right? You can have a quick picture here if you need, right? The same Baum series of the hydrogen spectrum will be like this now, right? This is the Zeeman and Stark effects. Zeeman or Stark effect. One line split to few more lines, right now. Okay, so such a thing was appeared. So that is another failure of the Bohr's model, right? Okay. Now let's come up with the solution. Let's come up with the solution for this thing. Let's come up with the solution for this one. Solution is very clear. Solution was very clear. Right? With this one, to explain this hydrogen spectrum, Niels Bohr proposed this kind of energy level diagram, no? To explain that this hydrogen spectrum, Niels Bohr proposed this kind of energy level diagram, no? N equals 1, N equals 2, the main principal quantum numbers. So ultimately comes towards the infinity kind of thing. No? This was the engineer diagram proposed by Niels Bohr to explain this one. No? Right? So the solution for this thing, this spectrum, is actually proposed by another scientist called as Sommerfeld. He came up with the idea Bohr-Sommerfeld model. With that, actually the idea was to explain this. What he has done to this thing was actually he had modified the energy level diagram done by Niels Bohr like this. He had introduced the sub-energy levels. These are the energy levels, no? These are the energy levels, no? The Sommerfeld, the next scientist, came up with the model, next atomic model, the Bohr-Sommerfeld model, had introduced the sub-energy levels to the atom. That means he said, look here, with the second energy level, you have sub energy levels. That means the second energy level, this thing is made out of two sub energy levels like this. The third energy level is made out of three sub energy levels like this. That was the idea. Fourth energy level is made out of four sub energy levels like that. Introduction of the concept of sub energy levels. Right? Ultimately, you come towards the nuclear infinity line, right? The idea is that, right? Anyway, this is the modification done to explain the Zeeman and Stark effects, the introduction of sub-energy levels. So the sub-energy levels given another quantum number. This is the principal quantum number proposed by the Niels Bohr, right? To identify the energy levels, the sub-energy level, to identify the sub-energy levels or the subshells, to identify sub-energy levels or subshells, he proposed the Sommerfeld proposed the second quantum number, the L value. Here, the second quantum number, the L value, the L values. Here, the L is 0, L is 1, L is 0, L is 1, L is 2, like that. The sub-energy levels are given the second quantum number, which is known as the azimuthal quantum number. Right? With this modification, they were able to explain the origins of hydrogen spectrum even in magnetic and electric fields. Right? So that was the solution given to the Zeeman and Stark effect. The first energy level contains only one subshell, orbit. So second energy level contains two subshells. Third energy level contains three subshells. So you would clearly explain the origins of few lines. So you see, earlier it was one line from n equals 3 to n equals 2. Earlier it was one line. But with this concept, you can clearly see, right, few more lines are appearing. Few more lines are appearing. With that, the guys were able to explain the origins of these splitted lines. Or one can say they explain the origins of Zeeman and Stark effects. So earlier it was one gap between the n equals 3 and 2. Now you have few more gaps. So you can think of few lines are appearing. Right? Even with these, you can think of few more lines are appearing. Right? So that is how they have explained the Zeeman and Stark effect. Right? That idea is there with the next page. Let's go to that. Right? The solution for the Zeeman Stark effect, right? Bohr-Sommerfeld model. It is said here. There. Let's go to the stuff quickly. Bohr-Sommerfeld model. It says Bohr-Sommerfeld theory described the atom in terms of two quantum numbers. The principal quantum number as well as the azimuthal quantum number, the L values. Bohr-Sommerfeld theory describes the atom in terms of two quantum numbers. With this extension, the theory provides an explanation for Zeeman and Stark effects. With this explanation, theory provides an explanation for Zeeman and Stark effects. Right? So next point it says, with this model, they introduced the concept of subshell. These are subshells. These are the main shells. KLMN, the main shells. Right? These are subshells. Subshells are referred to as S subshell, P subshell, D subshell. You may have heard about these things, subshells. So, the introduction of subshells done by the Bohr-Sommerfeld model. right? Subshells. See, with this model, they introduced the concept of subshells, and the second quantum number L, the Asymmetric quantum number, was introduced to describe the subshells, right? The second quantum number L was introduced to describe subshells. So it's like this: the quantum number and the subshell. So you have few subshells, right? S subshell, P subshell, D subshell, F subshells. So the asymmetrical quantum number with those is L equals 0, L equals 1, L equals 2, and L equals 3. Right? So the idea of subshells is actually introduced by the next model, which is known as the Bohr-Sommerfeld model. That was actually an explanation given to the Zeeman and Stark effect, which was a failure with the Bohr's model. Right now, so that is the introduction of sub-energy levels, that concept. Right now, okay. So this is a bit of a more idea, right? I mean, some knowledge for you to have, right? They won't ask questions from this area, Laman. They won't ask a question from this area, but I included this thing. I included this one. You should know about the Zeeman and Stark effects, right? They won't ask about the Bohr-Sommerfeld model, but I just included that thing for the continuity of the discussion. Because we are actually discussing about the story of the atom. We are actually discussing about the story of the atom, right? So if you are not mentioning this model, looks like there is a vacuum of the story, right? That is why I just included the Bohr-Sommerfeld model when we are discussing the story of the atom, right? That's all. So simple idea. Just have a knowledge on that as well, right? Okay. They won't ask questions about the Bohr-Sommerfeld model either, right? Okay. Right now, do you have any questions regarding the stuff learned so far? So
Yes, sir. So that is the N1, N2, N3, the main energy level.
yeah.
Then after that, the sub-energy levels, first one does not have the sub-energy level.
Yeah.
Second energy level N2 has one sub-energy, right? So as the number increases, 3 and 3 sub-energy.
Yeah.
Four sub-energy levels, right?
Yeah, that's correct.
Even goes, sub-energy level, they are named SP, SPDF.
Yeah.
Then after that, now in the third sub-energy level, sorry, fourth one, there are 4 energy levels. So SPDF, no?
Yeah, right.
Then the fifth one, SPDF, what is the name for the fifth one?
Yeah, okay. Right, it's a good question. It's like this, Chris. The idea is this. So basically, up to date, right, they have found only 120 elements. They have found actually not 120 stable elements, right? The stable elements are almost 100. After that, those are not that much stable, right? Those are experimentally produced at the laboratories only, right? They are not existing for long. Anyway, even in laboratories, they were able to produce up to 120 elements, right? Beyond that, still no evidence of having such atoms beyond 120 electrons, right? So when considering those 120 electrons with the 120th element and the 120 electrons, the existence of 4 sub-energy levels, will be enough to explain the electronic structure of 120 electrons. To explain the electronic structure of 120 electrons, which is the greatest atom theoretically possible, right? So that 120 to explain 120 electrons existing in an atom, only 4 subshells are enough. That is why they haven't mentioned another sub-energy level. But if you think of such, if you are go beyond, if you have found any atom beyond 120, 121st, 122nd, those elements, we may have to introduce another subshell. Some scientists are proposing that could be the G subshell. Just the number, right? Just later. So up to now, up to date, only 120 elements are existing, so that existence of 4 subshells will be enough. So n equals 4 contains SPDF subshells, n equals 5 also contains only SPDF subshells, n equals 6 also still contains SPDF only 4. That's all. You are not going beyond that, beyond F subshell, because those are enough. Those 4 kind of subshells are enough to discuss about 120 elements. I think you are okay with that answer? Is there? Okay, right now? Right. So that's the idea. So any other questions, Laman? If not, we can continue. Right, okay. Let's continue, right? Okay, now we are going to discuss about the most interesting part of the today's lesson, right? Okay, right. So actually Bose model failed. We had discussed about the reasons. Okay, then what is the model we are following today? What is the model we are following today? Is that the Bose model? No. You may have learnt about the Bose model in your O-levels, 288 structure, totally concentrating on the Bose model, 288. But nowadays, Bose model is gone, right? Even with 1920, 1925, 1927, when the 1925, 1927, those ages, still they have rejected the Bose model completely. Nowadays, we have a model called cloud model. Do you guys hear that? You may have heard about the cloud model, right? Our model nowadays is actually cloud model, not the Bose model. Have you heard about that thing, anyone? Lavai? No? Cloud model of atom? Actual Lavai, it is almost 100 years now. It is almost 100 years now to our existing model, the cloud model, right? Still you guys won't hear that, right? Okay, surprising, right? So our new model, right? Quantum mechanical atomic model, which is also known as the cloud model, right? Now we are going to discuss about that thing, right? Quantum mechanical atomic model now. Quantum mechanical atomic model. Right, which is also known as the cloud model. This model was finalized normally in 1927, those ages, right? From 1930 onwards, they have started constructing this model with the failures of the Bose model. They have started thinking of a new model after 1913, right? So they have finalized this model basically in 1926, 27 ages, right? So this is the cloud model, almost 100 years now, right? That is our modern atomic model. Let's discuss about that thing and what was the origins, how it came to the world, what was the story behind this model, right? Let's discuss about that. This is a very important model. We'll discuss the importance as well when the story goes on, right? Okay, the idea is this. So Bohr model failed, right? And I with that story, story of Tatio story or the flat man story, I said about kind of an unknown person. Actually, that unknown person that age was none other than Louis de Broglie. Right? He was the major scientist, one of the major scientists put forward some ideas to fail the Bose model. Let's discuss about his idea. Louis de Broglie said what he said, We had discussed that thing when we are discussing about the electromagnetic waves, right? Lewis de Broglie said that if you can say that waves are having particle nature, if you can believe that which Einstein said, which is actually waves are having particle nature, that particles like electrons should also have waves. That was the Lewis de Broglie's idea. Particles like electrons should also have waves, wave properties. Particles like electrons should also have wave properties. That was finalized, no? He proposed some equation as well, no? De Broglie's equation, the lambda is equal to h over the momentum, right? Okay. Then he questioned this. This is the question raised by the de Broglie. According to Bohr's model, the model was like this, no? This is the Bohr's model, no? With the Bohr's model, in 1930, right? Electron is actually maintaining a constant distance. From the nucleus. Constant distance from the nucleus. That means electron is occupying a definite space. Electron is occupying a definite position. Occupying a definite position. Occupying a definite position from the nucleus. This system is same, right? So electron is occupying a definite position from the nucleus. From nucleus, it is situated, let's say, from x nanometers distance. Definite position. Maintaining a definite position from the nucleus, according to Bohr's model. The de Broglie's idea is this. De Broglie questioned that as electrons are also waves, electrons are also having wave properties. As electrons are also having wave properties. As electrons are also having wave properties. Also having wave properties. Right? Actually, when it comes to waves, those are not maintaining a definite position. Definite position is maintained by particles. Definite position is maintained by particles. When we are discussing about the E equals mc squared, I have explained that thing. The difference between the waves and particles. Both are carrying energy. The waves and particles both are carrying energy. But when it comes to particles, the energy is localized. When it comes to particles, the energy is localized. When it comes to particles, the energy is localized. But when it comes to waves, the energy is spreaded throughout the space for the waves. Right? So the definite position is with particles. This is definite position. Some definite position is for the particles. But when it comes to waves, those are not having a definite position. Those are spread out. The energy is spread out through some space. So waves won't have a definite position. So that electron can't occupy a definite position from the nucleus. It can't have a constant distance from the nucleus. Constant distance from nucleus means you are maintaining a definite position from the nucleus. That can't be, as electrons are also with wave properties. As electrons are also with wave properties, that can't be. You can't maintain a definite position from the nucleus, definite distance from the nucleus, as you are with wave properties as well. The electrons are with wave properties as well. So that this can't be accepted. This can't be accepted. That was the logical point put forward by the de Broglie. Right? As electrons are with wave properties, those can't have a definite position from the nucleus. Those should spread out through the space. Those should spread out through the space. That is the wave property. Energy is spread out through the space, not like particles. So that was the case. Right? So then let's discuss about the points furthermore. This was the first failure. That was the failure proposed by the de Broglie. Let's write this stuff and then we'll come up with the solution. First write the few things there, what we have discussed, then we'll come up with the solution for this model, right? For that problem. Let's write this stuff. Let's write. See, quickly write, right? This is about the quantum mechanical atomic model, electron cloud atomic model, or the modern atomic model. Let's write this stuff, right? What de Broglie said, right? Put a star mark and write. With the de Broglie's idea of electrons behave as waves. With the de Broglie's idea of electrons behave as waves. With the de Broglie's idea of electrons behave as waves. With the de Broglie's idea of electrons behave as waves. Then a big question arises. 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 Right? In the next line within inverted commas, you can write this thing with a different color. You can write this question with a different color in within inverted commas in the next line, right? How an electron, this is the question arised by the right? Sorry, by the de Broglie, right? How an electron, a wave, a wave can have a definite position. How an electron, a wave can have a definite position. As electrons are behaving as waves also, right? So how an electron, a wave can have a definite position. Put a question mark. Close the inverted commas. Right? How an electron, a wave can have a definite position. Next star mark.
Excuse me, sir.
Yes, Deshana, yeah. Yes, same question.
Can you repeat that sentence?
Okay. With the start or just the question, Deshana?
With the start.
Okay, it says with the de Broglie's idea of electrons, behave as waves. With the de Broglie's idea of electrons behave as waves. Then a big question arises. With the de Broglie's idea of electrons behave as waves, then a big question arises. Then you can write it in inverted commas, right? And write how an electron, comma, a wave can have a definite position. How an electron, comma, a wave can have a definite position. Question mark. Close the inverted commas. how an electron, a wave, can have a definite position. Are you okay with that definition?
Yes, sir. Thanks.
Right, okay. Right, then write it with the next star mark as the next point, just write. Unlike in particles, this idea, unlike in particles, we cannot define a definite position. We cannot define a definite position. Unlike in particles, we cannot define a definite position for a wave. Again, I'm telling you now. Unlike in particles, we cannot define a definite position for a wave as waves spread throughout some space. As waves spread throughout some space. Right? Unlike in particles, we cannot define a definite position for a wave as waves spread throughout some space. The energy of them within brackets waves, the energy of them within brackets waves, close the brackets, also spread. The energy of them within brackets waves, close the brackets, also spread. Right. Put the next star mark and write this one. Now first we will write the story, then I will explain the stuff appearing there, right? First write the statement, after that I will explain the stuff, right? Okay, just write. Next point, right? With these ideas, according to write it in red color, quantum mechanical atomic model, write it in red color, quantum mechanical atomic model. With these ideas, according to quantum mechanical atomic model, in red color, right? Come to the normal color. Electrons in an atom do not have a definite location. Electrons in an atom do not have a definite location, but a probable 3D space do not have a definite location, but a probable 3D space where an electron density can be found. Right? Let's discuss about that idea. Right? That is clear. With these ideas, according to quantum mechanical atomic model, electrons in an atom do not have a definite location, but a probable 3D space where an electron density can be found. Right? Let's discuss that idea. The idea is this, Lama. idea is this. So now we are clear now that Niels-Bohr model can't be accepted. The Bohr model can't be accepted, right? That is clear. According to these wave ideas of the electron behaving as a wave, you can't accept the Bohr's model. That is clear. Now then what is the next model to come? What will be the next proposed model? That was the question those days. It is like this. The idea is this. Lamai, like in Bohr's model, right? Now we are clear the electrons are not traveling in orbits like this. Electrons are not traveling in orbits like this. That is not what is happening. Right? The idea is this. So actually that now I am going to discuss about kind of a mathematical idea, right? This is a mathematical idea. So this model, the quantum mechanical model, wholly depends on the mathematics. That's a kind of a mathematical idea, right? I'll explain those stuff clearly, right? When the story goes along, right? So it's a right. Keep it in mind. This is a mathematical idea. So I'll try to explain that idea with kind of a thought experiment. Right? Yes, it's a new term. Looks like thought experiments. Have you guys heard about thought experiments? No, not that much. Anyone heard about thought experiments? Please, do you have any idea about thought experiments? Thought experiments? No, yeah, right. I'll tell you. So in science, there are two major types of experiments. Right? So one kind is actually laboratory experiments. You know about those things. In small ages, also in O levels, you have done those. The lab experiments. Combusting kind of stuff, right? Adding some nitric to copper to produce some NO2 gas. KMNO for thermal decomposition to come up with O2 gas. Mixing two salts to come up with precipitates. So acids and bases are reacted to get some salts and water. Those stuff are actually referred to as laboratory experiments. You are very familiar with those experiments. Lab experiments. In physics as well, you have lab experiments. Chemistry, physics, biology. Science always with lab experiments. But when it comes to higher science, there is a experiment type referred to as thought experiments. Scientists like Einstein, Max Planck, those guys actually done some thought experiments. Those are very powerful tools in science, right? Thought experiments. Basically, all the experiment, the setup and the observations and all the experiment is actually carried in your mind. Thought experiments, right? Nowadays, these things are very easy with the existence of computers. Very easy to do these kind of thought experiments nowadays. But ancient days, right? There were no computers, right? The scientists came up with such thought experiments. I'll tell you the strength of these experiments. I'll give you some example describing the strength of these kind of thought experiments. Lamai, in 1915, almost 110 years ago, in 1915, Einstein proposed his concept of general relativity, which is known as a Sapekshataavadi in Sinhala, right? General relativity, Saman Sapekshataavadi, general relativity, right? When he is proposing his theory, general relativity, with a thought experiment, he proposed that there should be a very slight wave called as gravitational waves. There should be a very slight, right, wave kind should appear in our universe, and he referred it as the gravitational waves. And he said in 1950, right? In 1950, he said, right, I hope, even though this is existing, according to my mathematics, even though this is existing, according to my thought experiments with mathematics, even though this is existing, I wish and I suppose that the mankind won't be able to observe this. The mankind won't be able to observe this because such slight is the magnitude of those waves are. I am predicting that it is existing. According to my thought experiment, it should be there in our universe. But I doubt that the mankind wouldn't be able to catch those waves. Right? But Lamai, in 2015, in 1915, he proposed the idea of the gravitational waves according to his thought experiment. In 2015, after 100 years, scientists were able to experimentally prove the existence of gravitational waves. They got the Nobel Prize in 2017 for the gravitational waves. You can go to the concept. Just go to the concept. Gravitational waves. LIGO. Just search in your internet. They got the Nobel Prize for that thing in 2017. After more than 100 years. After 100 years, they found that thing. 2015. They got the Nobel Prize in 2017. Just check the Physics Nobel Prize, gravitational waves. You can clearly get the article from the Nobel community, nobel.org, right? That is the strength of thought experiments in science. As you haven't heard about that thing, I just explained a very little story about the thought experiments. The black holes and the kind of stuff, all are about thought experiments. Nowadays it's very easy to explore those things because of the existence of computers. But those days scientists actually came up with those ideas without any computer power. The experiments were proposed, done in their heads, ideas, thought experiments. I am going to explain another kind of thought experiments to grab this theory clearly about our new atomic model, the existing atomic model, the modern atomic model. I'll give you a thought experiment to grab the idea. Right? Okay. Right. Let's think of this is the story. Let's think of a camera, right? Which can give you million frames in one click. Let's think of a camera which can give you million frames in a one click. In a one click, million frames. That could not be possible up to date. But I wonder it will be there in 10 or 15, 50 years. Definitely. Now the technology is highly increasing, the developing. So nowadays, even with the iPhone, right, one click gives you 100 out of frames. That is why you clearly see the picture. So even when you are shaking, when taking the picture from iPhone, I only know about the iPhones, right? Sorry for that, right? So even you are shaking when taking a picture from the iPhone, still it will appear without blurring. You won't see the blur nature with the pictures of iPhones even you are shaking. Why is that? Because in one click, in 1 second, they will give you, they are taking 100 odd frames and they will process that thing and give you the output. Right? So such things are available nowadays, even with 1 click 100 frames kind of things, right? But I suppose I am now with our thought experiments, let's think of such a camera but not 100 frames but giving you million frames in 1 second with 1 click. Think of that kind of a camera. This is our experiment, okay, right? And then isolate and one single hydrogen atom. That can't be done, right? Okay, only in our minds we can do, you can come up with such experiment, right? Just isolate one hydrogen atom. Last day we had discussed. If you have gone to the last day's theory, listen, you will see how hard to isolate such kind of hydrogen atom. It is not possible to date. It is not possible to date, but I wonder it could be happen in 100 years. It could be happen in 100 years. Some scale produced to measure for the 23rd decimal could happen in 100 years. Okay, you should have those two equipments to do this experiment. That is why I am referring this as a thought experiment today. It won't be in 100 years, right? Okay, you have isolated one single hydrogen atom and you have a camera which gives you million frames in 1 second with 1 click. And what you need to do is just take a one click, one picture, 1 click, that means million frames from your camera of your isolated single hydrogen atom. What it will be looks like. Let's discuss about that. That is all about this theory, right? It will look like this, right? This will be the nucleus. I had just taken million frames from our camera, from just 1 click, right? In your first frame, the electron would appear here. In your first frame, the electron would appear here. In your second frame, the electron would appear here. Third frame, you have million frames. Fourth frame, fifth, sixth, seventh, 8, 9, 10, 11, 12, 13, 14, 15, 16, like that. In your frames, the electrons are appearing here, 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 here. One single frame is with one single electron. Another frame, electron will be here. Next frame, it will be here. Next frame here, because the hydrogen atom contains only one electron, right? At the next frame, it is here, the one single electron, the position of that electron. In the next frame, it is here, 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 here. Next frame here, here. Another frame, that one single electron will be here. Nucleus is always appearing at the same position for all the frames, right? Here, here, here. So then you clearly see the appearance of electrons in all the frames. And what you need to do is, you have to, right, take all the frames. You have to take all the frames then. And just overlap all the frames. Just put one top of the other. Just put one top of the other, one top of the other, one top of the other. All the million frames, put like that. Then you will see this picture appearing. Right? This is the picture of the hydrogen atom. You don't have million electrons here. You just have only one electron. At one frame it is here, at the other frame it is here, at the other frame it is here, next one here, here. If you are to put all the million frames on top of the other, you will get this picture. This is so hydrogen atom. So, right? So, the maximum probable space, normally we refer to as the 95% of occasions which you can find out the electron, that maximum probable space, where you can find out the electron. Those should include 95% of electron appearance. If you are to border that space like this, it is referred to as a atomic orbital. Atomic orbital. Atomic orbital. So with this model, you don't have orbits. You don't have orbits. What you have is actually orbitals. 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 What is an orbital? Orbital is the maximum probable space where you can find your electron. Find your electron. This is the concept for orbital. Concept for orbital. This is your hydrogen atom. So according to this thing, one can say it is like this. This nice phrase comes to my mind, right? This is referred to as the cloud model. This is referred to as the cloud model. This is the cloud model. Cloud model of your atom. Why we refer to this as the cloud model? Cloud model. Planetary model, plum pudding model, nuclear model, golf ball model. Like that, this is cloud model. In simple words, it's cloud model. So it is like this now. So have you heard that very famous quote? I think from Nicholas Spark. Love is like the wind. You can feel it, but you can't touch it. Right? Like this, our electron is like the wind. I can feel it, the existence, I can feel it, but I can't touch it. When I am thinking of touching the electron from here, it won't appear no longer there. It will be here, or here, or here. When I am thinking of touching my electron here, when I see that electron appearing here, I just need to touch that electron. No longer it won't appear there. It will be anywhere else. This whole thing is in a 1 second. Such speedy movements are with the electrons, right? So I can feel the existence of electrons, but I can't touch that. Like a cloud, like a cloud. You see the clouds appearing. Can you touch them? The mist appearing, you see. It is there. Can you touch that? No. That is our atomic model. So this is about your hydrogen atom, the normal hydrogen atom. This is not the excited hydrogen atom. But if you had excited your hydrogen atom and took the same picture, that one click, which gives you million frames with any kind of excited hydrogen atom, you would be able to see some different patterns also. With excited hydrogen atoms, I'll write another pattern here with excited hydrogen atom, right? So if you have to take an excited hydrogen atom, this is from a ground state hydrogen atom, right? If you think of an excited hydrogen atom, it will look like this. Sometimes the thing will look like this. This would be the nucleus. The electron will appear here, 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 with million frames, right? With one frame here, the other frame here, 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 next one here, here, next frame here, here, like that. In frames, electron will be appeared at these positions with a kind of excited hydrogen atom. These positions, electrons are appearing, right? So if you have to take all the million frames into one picture, if you are to put them one over the other to take a one picture, process for one picture, things will be like this. See, what is the shape there? if you take the 95% of appearance of the electron and border that space, you will see this thing. Another kind of orbital, another kind of orbital, another kind of orbital, atomic orbital. Maximum possible probable space where you can find an electron. When the shapes of the orbitals are different, when those are different, when those carrying with different shapes, right? Those orbitals are named as s orbitals and p orbitals, like that. So these are the s orbitals, the spherical shaped orbitals. These are the p orbitals, dumbbell shaped orbitals, like that. In d subshells you have d orbitals, another shape. F subshells you have another kind of orbitals, f orbitals with another kind of shape. So with this new model, the cloud model comes up with orbitals, not like orbits in Bose model. In Bose models, those are orbits, 2D concept. In your cloud model, it comes with orbitals, 3D model. This is the kind of a spherical stuff, right? It's not 2D Lama, it's spherical. Spherical. These are spherical, dumbbell shaped spherical. Sorry, this is a dumbbell shaped 3D. This is spherical, not a circle. It's a spherical, 3D stuff, right? So this is kind of a 3D model explaining our atom, right? This is the idea. This is our new atomic model. We can feel the existence, but we can't touch, right? Actually, these waves, these kind of waves are given a specific name. So when it comes to wave nature, you always come up with these kind of things. No, that what comes to your mind. No, waves. Okay. But these are referred to as special kind of waves. These are known as standing waves. These are known as standing waves. In our modern atomic model, we are referring to standing waves. Lamai, you are going to learn about standing waves in your physics lesson. Unit number 3, waves and vibrations. In your physics lesson, unit number 3, in waves and vibrations, that lesson, you will learn about standing waves, about these waves. You will learn further the mathematics and the stuff about these waves. Standing waves, properties and the stuff. You will learn in A-levels. So this won't be a new thing when you are to sit in your exam, A-level exam. Those will be studied in your physics lessons, right? Standing waves. I'll give you some idea about standing waves also. I'll give you a bit of idea about standing waves also. Actually, standing waves are not kind of unusual stuff. Standing waves appear, you can create standing waves in your home as well. You can think of standing waves appearing in your home as well. Right? I'll give you a little example. I'll give you a little experiment to do at your home. Right? So take a rope. I'll go here, come here. Right? Take a rope. Right? And take a rope and bind that thing. 2 points. Take a rope and bind that thing to 2 points. Bind that into 2 points. This is a rope, right? This is a rope. Right? අර ළමයි ඔයගොල්ලෝ අර මේ අර ඇඳුම් එල්ලන්නේ අර ඇඳුම් එල්ලන වැලේ තියෙන්නේ ආයෙ එක කරන්නකො කවන්නේ හරි ඇඳුම් එල්ලන වැලේ තියෙන්නේ ආයෙ let's consider that thing where you hang your clothes, right? Take that rope, okay, take that system. Hurry, this is about the standing waves. Hurry, then pull this one, pull this one and release. Pull this one and release and see what will happen. Pull this one and release and see what will happen. What will happen now? This will come upwards, come for this confirmation, and for this confirmation then, and come for this confirmation, this. You will see this kind of thing will appearing. Standing wave. Standing wave. Up and down, standing wave. You can look at this. You can do this experiment. Standing waves are actually when waves are actually waves are in two. Actually, waves are, we can say it like when waves are concentrated, though when waves are confined. That's the good word. When waves are confined to 2 points, when the waves are confined to 2 points, the standing waves appear. Right? So this is a kind of standing wave. So you can clearly see the rope is coming up and down and this stuff, right? You can see it's like a cloud. When you are thinking of touching the rope, when it is coming here at this point, when you are thinking of touching the rope at this point, actually you won't touch the wave at that instance. It is traveling. Maybe we won't touch that. But when it is coming again to that point, you will touch. But it is hard to touch the rope. Right? You see that. You feel that. But you can't touch that. Standing waves. Right? The same concept with this one. This is a little experiment, right? Which can be done with your home. Right? So, that is our new atomic model. Lamai, actually this is the reason for all the technology today. This model is the reason for all the technology you see at this age. Such a powerful model. Right? So, earlier days, our let's think of the mobile phone. Earlier days, think of the mobile phone. Just ask from your mother or father, not from mother or father. Just ask from your grandmother or grandfather about the mobile phone first introduced to the world. Right? They will say it looks like a. They will say that it looks like a brick. A gadol bagak wage. Aheva kiyai. Will tell you that it's like a brick, half of a brick or something, like a gadol bag. Such large is your mobile phone when it is coming to the world. But only one thing can be done with the mobile phone. What is that? Just taking a call. Only what we can do with that mobile phone is just taking a phone call. The size is this much. It is very hard to associate with. But nowadays, what about the mobile phone? What about size? Nowadays, we are thinking of AI pins, AI glasses, which we can call and the stuff, all the things can be done. Actually, Lamai, with this era, with a mobile phone, actually what is the thing we can't do? Give me one thing which we can't do by a mobile phone. Earlier days, only a call can be taken with such a large phone. Nowadays, the mobile phone is very small. Even they are trying to introduce kind of a thing called as AI pin, such as small stuff that can be pinned here, right? So the screen will appear virtually. You can go to virtually. You can take calls by just saying the name Even Siri will do those things nowadays. No need to point any of numbers or anything, right? You can just say call Siri, just call Amma, just call Tata. The phone call will ring. You can say just hey Siri, just send him this message. Send Tata, I am late, I will be late today. He will send the message. Tell me one thing which we can't do by a mobile phone nowadays. There's a story called as when it comes to JR's constitution. There was a very famous saying, no? With the JR's constitution, what we can't do is just converting a man to a woman. That is the only thing we can't do with the JR's constitution. That's such kind of a thing is there, no? Such kind of a race is there, no? But nowadays, with a mobile phone, even we can convert a man to a woman. That thing also can be done. See, all the things, all this technology is possible because of this theory and the nanotechnology. Nanotechnology totally right on this theory. Without this theory, you can't think of nanotechnology. Right? So that much of a powerful theory here. Right? That is our modern atomic theory. That is why this is lasting almost for 100 years. Right? That is our atomic model, our proud model, the cloud model. Right? Okay, let's complete the note here, the last lines of the note. Right? So, do you have any questions regarding this one, Naru? So, this is our new model. Okay, let's go to this, right? So, we'll complete, right? Lamai, we had written the third point as with these ideas according to quantum mechanical atomic model, electrons in an atom do not have a definite location, but a probable 3D space where an electron density can be found, right? That is okay, right? Then under that within inverted commas, under the same topic and under the same point within inverted commas, right? Just write in red color about this orbital concept, right? Just write it in red color. The probable 3D space, where we can find an electron, write it in red color, the probable 3D space where we can find an electron, the probable 3D space where we can find an electron, the probable 3D space where we can find an electron, within brackets, right, within brackets, electron density where we can find an electron, within brackets, electron density, close the brackets, is called an orbital, is called an orbital is called an orbital. I'll tell you again, the probable 3D space where we can find an electron, within brackets, electron density, is called an orbital, close the inverted commas, right? Close the inverted commas. That is the idea, right? This is our modern atomic theory, right? With these things, all the problems vanished. This can explain the multi-electronic systems. This can explain all the atomic spectra appearing with any kind of electronic system, not only for one electrons but also for multi-electronic systems, helium, neon, argon, lithium, for all the atoms, even for hydrogen atom, right? For all the atoms, we can use the origin of those spectra, right? So this solves all the problems appeared with the Bose theory, right? Okay. Put the next dash, put the next star mark and write. Put the next star mark and write with the normal color. Just write these orbitals within brackets, electron densities electron densities. These orbitals within brackets electron densities, close brackets, each having different shapes are of 4 types. Each having different shapes are of 4 types. Each having different shapes are of 4 types. These orbitals within brackets electron densities, close brackets, each having different shapes are of 4 types. Right? Are of 4 types. Let's write those things, right? Are of 4 types. Right. Just draw this one, Lamai, with me. Right. You have spherical orbitals, which are known as s orbitals. You have dumbbell shaped orbitals. It's like dumbbell, no? Dumbbell shaped orbitals, right? Okay. Then you have double dumbbell shaped orbitals, 2 dumbbells connected. Double dumbbell shaped orbitals. And you have some complex shaped orbitals as well. This is hard to draw here. Complex shaped orbitals as well. Right? So spherical orbitals are referred to as s orbitals. Right? Spherical ones are referred to as s orbital. And dumbbell ones are referred to as p orbitals. Now with me, just write this stuff, just do this stuff. Referred to as p orbitals. Now these SPDF are simple letters, right? SPDF are simple letters, right? Simple letters. And double dumbbell stuff are referred to as d orbitals, and complex shape stuff are called as referred to as f orbitals. Just draw this one. Right. Quickly draw this one now. Right now. Spherical. These are all of these guys things are 3D, right? 3D structures. Spherical shaped, dumbbell, double dumbbell, and complex shape. Right now. Okay. Actually, that is the end of our first tute. Right? With this, we are completing our first tute. Right? Okay. Next, we'll go to our next tute, which starts with the quantum numbers. Right? Do you have any questions, Lamai, regarding this one? Right? Regarding the sections we have studied today. Do you have any questions before we go into the next section about the quantum numbers? Right? If you have any questions, you can ask. Just complete this stuff as well, right? Right. Clear, na? Yeah. Yes. Hmm. Yeah, okay. Is that all? Yeah, that is the question. Okay, good one. Next. Is that all? Is that all?
Yeah.
Ah, okay, right. Yes, the relationship between the subenergy levels and the orbitals, that was the question. Yes, clear. It is like this, Lama. So I'll tell you something. This will be discussed with the next topic, the quantum numbers. But before, yeah, as you are asking, I'll tell you. Like this, no. So you have energy levels like this and sub energy levels. So let's take right. These are n values. N equals 1, n equals 2, n equals 3 stuff. Right. Then I'll draw it with some space because I need to explain further. N equals 3, so n equals 2 appears like this, n equals 1 like this. Okay, so this is L equals 0, L equals 0 and L equals 1, the sub energy levels, the second quantum number. The idea is this. So orbitals are the maximum probable spaces where you can find your electron. These are the maximum probable spaces where you can find your electron. Right? So in your energy levels you have orbitals. Sorry, in your sub energy levels you have orbitals. Let's simply I refer them like this. Some sub-energy levels are with only one orbital. Some sub-energy levels are with more than one orbital. So when it comes to p sub-energy level, it has 3 orbitals. When it comes to s sub-energy level, S subshell only one orbital is there. That is the relationship, right? When it comes to p sub-energy level, you have 3 orbitals. When it comes to d sub-energy level of the subshell, you have 5 orbitals, maximum probable spaces where you can find your electron, 5. So these orbitals are these. In S subshell you have spherical orbital. This is kind of a spherical stuff. These are kind of dumbbell stuff. These 3 orbitals are dumbbell orbitals. In p subshells you have p orbitals, those are dumbbell shaped. In d subshell you have d orbitals, those are double dumbbelled in shape. In S subshell you have only one orbital, it is a spherical shaped orbital. Right? That is the relationship between the orbitals and the subshells. The orbitals means the maximum probable space you can find out your electron. So orbital basically carries some idea about the space as well. In your energy diagram basically the energies are mentioned, but orbitals carry some idea about the space as well. Are you okay with that explanation, Chris? Do you have any other questions? Right, no? Okay. Right. We'll discuss that thing a bit more at the same stuff when we are doing the quantum numbers as well. Right. Any other question? Right, no? Okay. Then we'll go to the next. We'll go to the next section with the next tute. I think some of you haven't received that thing. We'll quickly give it to you, right? And we go to that tute. Let's start. Before that, give me 1 minute, Lama. I'll have a drink, right? I'll have some water and come to the class, right? So go to the next tute. We'll start with that, right? Okay, Raman. Let's start the discussion on quantum numbers. Right. Okay. My class will go till, yeah, we have some 40 odd minutes, right? We'll do that thing, right? Okay. Quantum numbers. Yes, first of all, let's discuss why we need this kind of concept. Before going to the quantum numbers, okay, let's discuss why we need this kind of a concept, why we need some kind of concept as quantum numbers or something, right? Okay, so the idea is this, Lamai. So according to Bose model, when it comes to the Bose model, right? When it comes to Bose model, right? If you have two, let's consider you have two electrons. One is here, the other one is here. Two electrons. Let's think of a one frame from your medium frame picture of an atom with two electrons. Let's think of the helium atom. You got a one click from your medium frame camera, okay, and you had seen the two electrons are appearing like this. So according to Bose model, if it is according to Bose model, right, if you think of the energy of this thing and the, I'll take it as red, it is not red colored only, right? I'll just for the convenience I'll just take it as it, right? According to Bose model, we can say that the energy of the red electron is actually smaller than the energy of the blue electron. According to Bose model, one may think like this, because this thing is more close to your nucleus, this guy is more away from your nucleus. So if two electrons start to appear like this in your atom, one may think that this electron carrying some lesser energy than this electron. If you are thinking according to Bose model, the electron which is closer to your nucleus is with a lower energy, which is away from the nucleus is with a higher energy, according to Bose model. But the thing is, Bohr model is not the truth. It is not explaining the truth. Right? This is not explaining the truth. We can't confirm about this. Actually, we don't know about this. Truth is, we don't know about this. That is the truth. According to Bose model, one may think this is with a lower energy than this one. But the truth is, by merely looking at one frame, we can't decide that. Which is with greater energy or which is with small energy. Why is that? See, let's think of the actual stuff, actual probability. Right? So this is your atom, okay. This is your atom. This is your nucleus. Okay. Sometimes this red electron, this is a multi-electron atom, right? Don't think of that helium or any kind of multi-electron. Just think of excited helium. Excited helium atom. So your red electron could appear with this kind of a orbital, and I'll take the blue one here, and blue electron will appear with this kind of orbital, right? So if the energy of this thing, energy of red thing, is actually greater than the energy of blue thing. See the actual probabilities. So E could be a position of this orbital. If you are to take the million frames, if you are to take the million frames of the red electron, it could be like this. It has more ability to occupy a space which is far away from the nucleus. The red color thing can have more probability, to occupy some space away from the nucleus than the blue color thing. So if the orbitals are appearing like this, it says, right, the red electron is having greater energy than the blue electron. Or else, the other thing also could be possible. This is your atom. This is your atom. So the orbital of the red electron could be a smaller one than the orbital of the blue electron. If you have to take the million frames, this could be the situation. In this one, right, the blue electron is with a greater energy than the red electron. So actually, just looking at one frame, we can't decide actually which electron is with which kind of energy, which is with greater energy and which is with a lower energy. We can't decide that thing because our truth is far away from the Bose model. Our truth is far away from the Bose model. Truth is not the Bose model. If the atom is according to Bose model, when you are with a greater distance, your energy is high. When you are with a smaller distance from the nucleus, energy is low. But nowadays we know it is not the model. It is not the truth. This is the truth. So even though you are appearing at a smaller distance to the nucleus in one frame, still you can have a greater energy if you have to consider the total orbital with million frames. See, so that by merely considering the position, by just considering the position of an electron, you can't decide about its energy. That is the idea. According to this model, according to our new atomic model, according to our cloud model, by just looking at the space, by just looking at this position of your electron, not the space, but by just looking at this position of your electron, you can't decide of its energy, whether it is a higher value or a lower value, according to this model, according to our acceptable cloud model. Just by looking at the position of the electron, you can't decide whether it is with a great energy or a low energy. So that we should come up with a better way. We should come up with a better way to give the properties of your electron. By just looking at this position of one frame, you can't decide about its orbital. You have to take million frames for that. Right? So we should have a method. To extract information of this electron we should have a method to extract information of these electrons. For that, we use quantum numbers, the set of quantum numbers. Actually, Lamai, the set of quantum numbers is like a barcode for your electron. The quantum number set is kind of a barcode of your electron. If you have a better barcode reader, if you have a good reader, barcode reader, you can gather all the information of your electron by just scanning that barcode. That is the idea. You know about the barcodes, right? Nowadays we are using QR codes, no? But still the barcodes are using, right? So you just go to the Keys Super, inside kind of a thing, right? Supermarket with all the food containers and the stuff. The barcode, kind of a barcode is appearing even in books stuff, right? So you can scan the barcode, and that barcode will give you all the information about the product, no? The manufacturing date, the price, and the expiring date, the ingredients, all the things will be included in the barcode, right? So if you are coming up with a good barcode reader, you can gather all the information about the product by reading the barcode. Like that, the quantum number set, it is carrying 4 numbers. A quantum number set of your electron is like the barcode of your electron. If you have a good reader to read the barcode, you can gather all the information about the electron with that quantum number set. It is like the barcode of electron, right? By just applying the by just reading the barcode of this electron, you can gather the information about the energies, about the orbital, the shape of the orbital of that electron, and about the large or small, the size of electron, size of orbital, about the size of orbital, about the shape of orbital, about the energy of the electron, about the spin of the electron. All those 4 informations can be gathered by its barcode, the quantum number set, right? So now we are going to study about the quantum numbers, right? Right, it's the barcode of electron, right? Let's study. So it says, go to the note, Lamai, your note, it says quantum numbers, and it says, with the identification of the energy levels, quantum numbers are used to describe the probable electron density of an electron. With the identification of energy levels, quantum numbers are used to describe the electron densities of your electron, right? Then it says here, the quantum mechanical model uses 4 set of quantum numbers to completely describe or identify an electron. To completely describe, to completely absorb the properties of the electron, quantum mechanical model use 4 quantum numbers. The principal quantum number n, the angular momentum quantum number L, that's a mutual one, right? The magnetic quantum number ML, and the spin quantum number MS. Those are the 4 set of quantum numbers we are using, right, to gather the informations about your electron, right? Let's study one by one, right? First one, the principal quantum number n. The principal quantum number n, right? Principal quantum number n. This is the quantum number which introduced by the Niels Bohr. The first quantum number, the principal quantum number n, right? Actually, we know about this quantum number now. We know about the first 2 quantum numbers. We had studied those introduced by the Bohr and the Sommerfeld, right? The first quantum number is the n value of your electron. Actually, that n value, the first quantum number, the first number digit in your barcode of quantum numbers, right? That will give the idea of the main energy level where the electron occupy, where the electron resides, right? The idea of the main energy level, right? That is given by the first quantum number, first number of your electron, of your barcode, right? Main energy level, right? Okay. Next, then it will give you some idea about the size of the orbital as well. It will give you some idea about the size of the orbital as well. See, so let's say you have 2 electrons. You have 2 electrons, you have two electrons where they comes up with some spherical orbitals. You have two electrons, right? You have two electrons, right? Two electrons coming up with spherical orbitals, right? Which is at the first energy level as well as the second energy level. The other one is at the second energy level. See, you are with an atom with two electrons. There is an electron at the first energy level spherical orbital and the second energy level spherical orbital. This is your n value. This is your n value, the energy level of the electron. So first energy level's orbital will be a smaller one, and the second energy level's orbital will be a larger one. The maximum probable space you can occupy is actually larger for the second orbital. So basically, this n value, both are spherical orbitals. The shape is same, but with the increasement of the first quantum number n, we can clearly see the size of the orbital increases. So the first quantum number gives you some idea about the size of the orbital as well. N gives us the first thing is n gives us the idea about the main energy level you are residing. The electron is in, or electron is occupying, right? And the same thing gives you the idea about the size of the orbital. When n is high, when you are with a greater energy level, your size of the orbital will be larger. The maximum probable space you can find out the electron is actually kind of a larger one, right? So if you are with some electron with third energy level, that maximum probability is even larger than here. So when the n value increases, size increases. That is the idea, right? So those are the main two things you should know about the n value. It will give you the energy level of the electron, or it will give you the energy, the main principal energy level, main energy level of the electron in your energy level diagram, and it will provide you the idea of the size of the gives you some idea about the size of the orbital as well. Then when the n value is large, the size is large, right? And then you can't have any value for n. The next point, you can't have any value for n. You can obtain only the positive integer values for n. That is proposed by the Niels Bohr, right? Niels Bohr said only the positive integer values are capable as n values. You don't have zeros as well. The energy levels, first energy level, second energy level, third energy level, n equals 1, 2, 3 like that. Only the positive integer values are possible for n. Those are the 3 points we should know about the principal quantum number, right? All actually some came from the Niels Bohr, and when it comes to orbital concept, such thing also appears, right? Okay, let's write the stuff. Let's write the 3 things we need to know, right, about the n value, the principal quantum number. Let's write. First point, under the principal quantum number n, you can write the first point. First point defines the come to the red color, red color. Main energy level defines the main energy level within brackets electron shell, within brackets electron shell. So in an atom you have energy levels, no, K, L, M, N. In small ages you may have heard about those things, right? That is what is represented by n, right? Defines the main energy level within brackets electron shell, close the brackets, that electron occupies in the atom. Come to the normal color and write, Lama. Come to normal color and write. That electron occupies in the atom. Defines the main energy level electron shell that electron occupies in the atom, right? Next point. gives an idea about the 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 come to the red color now, come to the red color. Size of an orbital. Size of an orbital. Gives an idea about the size of an orbital. Write it in red color. Size of an orbital. Size of an orbital. Under the second point, put a dash and write. Under the second point, put a dash and write. As n increases, the orbital becomes larger and as n increases, the orbital becomes larger and the electron spends more time further from nucleus. The electron spend more time further from nucleus. The electron spend more time further from nucleus. As n increases, the orbital becomes larger and the electron spends more time further from nucleus. Right? Electron spends more time further from nucleus, right? So, Lamai, right? You can draw this one. Quickly draw with me. So, if you take three spherical orbitals, 1s, 2s and 3s, right? So here your n value is 1. This is the first spherical shape orbital appearing in your energy level. This is the spherical shape orbital appearing in your second energy level. This is spherical shape orbital appearing in your third energy level. Right? So you clearly see when the size increases, when the n increases, the size will increase. Just draw this thing. The same thing applies for p orbitals as well, right? The second energy level's p orbital is smaller than the third energy level's p orbital. That is smaller than the fourth energy level's p orbital, like that, right? So that is the idea. So just draw this thing quickly. Right. Next one. Next point. Let's come to the next point. Right. You can write here. N can have come to red color, Lamai. Come to red color and light. Only positive integer values. Only positive integer values. Only positive integer values. Only positive integer values. Only positive integer values 1, 2, 3, some dots. N can have only positive integer values 1, 2, 3, some dots, right? So that is the restriction with the n. So you can write this thing as well. N will be equal to 1, 2, 3, some dots. All the four quantum numbers are with restrictions. All the four quantum numbers are with restrictions. So when studying, you have to study those restrictions as well. Right? So this is the restriction with the n value. So only positive integer values are available. Only counting numbers are available. That is a restriction with the first quantum number. Only positive integer values are available. Just write this thing now. Under that, just write n is equal to 1, 2, 3, like this. That is restriction. Right? Now, when studying quantum numbers, right, there are major three concepts to study. There are major three concepts to study when studying quantum numbers. And that is what we are doing with this session, right? The first thing to study is, first point is, what is actually it is about, what this quantum number is about. When it comes to n value, it is all about the principal energy level. It is all about the principal energy level of your electron occupying. What is this quantum number about? That is the first point. The second point is, what is the spatial idea? What is the spatial idea? What is the picture comes with the quantum number? Spatial idea, spatial arrangement and the spatial picture, the physical idea. What is the physical idea of the quantum number? That is the second point. In here, the physical idea is this. When the n value is large, your orbital is large. The physical idea. When n value is large, your orbital is large. The third point you should study is the restriction comes up with the quantum number. The restriction. With all the four quantum numbers, we are going to study about those 3 points. The restriction is this. Not all the values are possible for n, only the positive integer values. Only the positive integer values. Right? That is all about the n values. Right? It's all about the n values. Right. We'll come up with the next quantum number. And before that, do you have any questions regarding the first quantum number? Any other questions regarding the first one?
It's 1s, 2s, 3s. It's the radius are increasing. We can mark the energy levels that we did in the O level, no? That diagram we can use. It's the same thing, no, sir? That we are separating this one. No?
So it is like this. If you take the radius of the orbital, what you are saying is true. But radius of the orbital won't say that electron resides here. In your O levels, what you have studied was actually orbits. Two different things here. In your O level, you have studied orbits. Comes with the Bose theory. Orbits comes with the Bose theory. So electron travel through the radius of the orbit. If those are orbits, but these are not orbits. Remember, these concepts, quantum numbers comes up with the cloud model, quantum mechanical model, cloud model. These are not orbits, these are orbitals. Two different concepts, right? When it comes to orbitals, the electron is not always at the boundary. Electron is not at the boundary always. Electron can occupy anywhere of this inside this orbital. This is just giving you the maximum probable space where you can find your electron. So electron could be here, 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 anywhere inside this thing. Anywhere inside this thing. So in quantum mechanical model, you are describing the orbitals. That is what differs compared to the O-level stuff. In O-level stuff, you came up with orbits. Orbits came from the Bose theory. Right. Okay. Right. Next one. Let's come up with the next quantum number. This final quantum number. Some little stuff are there to discuss. Right. Let's go through that thing quickly. Then we can think of discuss the ideas about the third and fourth quantum numbers next day, right? We'll discuss the second quantum number as well, because these two quantum numbers are actually some known quantum numbers to us now. The quantum number described in the main energy level and the sub energy level, this PDF, the sub energy levels, right? We'll discuss about that thing as well to wind up the lesson. After that, we can discuss the new two quantum numbers at the next class, right? Let's come up with the L values. Let's come up with the L values. So L values actually gives you the subshells, no? Subshells. You know the idea about the subshell, right? So L values gives us the idea of the subshell, right? Let's write that thing. Got the idea, no? Let's write. I'll explain why it needed, right? just write the under the L values, first point, just write defines the this is about the angular momentum quantum number, right? Defines the come to the red color lamai, come to red color and write subshell, defines the subshell, defines the subshell, right? Within brackets, come to the normal color and write, within brackets come to normal color and write set of orbitals that have the same n and l values, set of orbitals that have the same n and l values, simple n and simple l values, is called a subshell. Set of orbitals that have the same n and l values is called the subshell. Right? Got the idea? No? So it's like this. No? Last time when Chris asked a question, I came up with this kind of picture. So I think you remember that thing. So if you are to come with n equals 2, these are the L values, L equals 0, L equals 1, sorry, L 0 and L equals 1. So it is all about set of orbitals which are with the same n and l values. Right now? That is subshell. This is subshell. Subshell means it contains set of orbitals with same n and l values. With these electrons appearing here and here, all are with n as 2 and l as 1. Set of orbitals having same n and l values. Those are referred to as a subshell. This is subshell. You would have such D subshells as well, right? We'll discuss about the subshells further at the next quantum number. We'll discuss more about the subshells at the next quantum number. We'll discuss that thing later at the next class, right? So that is some idea about for today's session, right? Next point. I earlier also said, Lamai, we need to discuss about 3 points on each and every quantum number. First thing is what is the quantum number is about. Yes, this quantum number is about subshells. This quantum number is about subshells. What is that quantum number is about? Second thing, what is the physical idea? Picturized idea. What is the picturized idea? Actually, the picturized idea of the L values is the shape. When the L equals 0, it is spherical shaped. This is a picturized idea. Yes, have that note as well. The picturized idea. Right? We need to come up with 3 points. No? What is the value is about? Then what is the picturized idea? Let's write that thing. Right? Just write. Gives an idea about the second point, Lama. Gives an idea about the shape of the orbital. Write it in red color. Shape of the orbital. Write it in red color. Shape of the orbital. Gives an idea about the shape of the orbital. Right? So you can quickly draw this one. L equals 0, L equals 1. The same picture, the same picture we have drawn earlier. Same picture. Right? When the L value differs, your shape will differ. Right? So these are s orbitals, p orbitals, d orbitals, and the f orbital. So you can copy the same picture. So spherical, dumbbell, double dumbbell, and finally the complex shaped. Right? Just draw this one. Spherical, L is 0. Then when you see when the L value changes, the shape of the orbital changes. That is the physical idea. That is the physical idea of your quantum number. L value. It's a physical idea of the azimuthal quantum number. Right? Then the L value change. So in this case also, when the L value change, the shape change. L equals 0 means spherical. All of these orbitals, 3 orbitals are dumbbell shaped. All of these guys are dumbbell shaped. This is spherical. Right? Sorry? 1, 1, 3?
Numbers how is increasing it. It is equal to 1 orbital. It is equal to the first L1 orbital and then 3 orbitals.
Ah, yeah, right. It will come with the restrictions, Chris. So I said all the quantum numbers are with restrictions, no? All the quantum numbers are with restrictions. When it comes to n values, only the positive integer values are available. When it comes to L values, right, some restriction is available. When it comes to M value, third value, another restriction available, right? So with due to the restrictions with the quantum numbers, basically what you have asked is about the ML value stuff, right? Due to that restriction of the ML values, right, with the P subshell, only 3 orbitals are available. With the S subshell, only 1 orbital is available. With the D subshell, there will be 5 orbitals available. That is actually due to the restriction in the ML value, the magnetic quantum number. We will discuss that thing at the next class, right? Wholly due to the restrictions of those quantum numbers.
So this and whatever we have given that 2, 8, 18, 32, that is connected with those.
Yeah, actually connected. It will be like 2, 8, 18 and 32. Yes, those are connected. You can get the clear idea, clear picture when all the 4 quantum numbers are done, right? So yeah, those are connected, right now. Right. So this is about the picturized idea or the physical idea about the L value, right now. So you can take a screen capture as well, right? Let's come up with the final point. The final point for today's lesson about the final point of the L value. That is all about the restriction of L value. I always told you 3 points are to be studied with all the quantum numbers. The third point is all about the restriction, right? Let's come up with that thing. Just write this thing, man. Write this thing and then we'll discuss, right? Third point under L, right? L can have simple L, right? L can have come to red color and write integral values from 0 to n minus 1. 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 So you can't have any value for L lamai. You can't have any value for L lamai. Right? You can have only the integral values from 0 to n minus 1. That is a restriction. L can have integral values from 0 to n minus 1 Come to the normal color. For each value of n. This is restriction with the L values. Right? L can have integral values from 0 to n minus 1 for each value of n. You can write this thing. Right? I'll give you the idea here. I'll give you the idea here. So idea is this. So if you take the main energy level, which is denoted by the n value, right? N values can have n equals 1, n equals 2, n equals 3 and n equals 4. Those are the possible n values. If you take those and the L values, which gives the subshells. My L value is under a restriction. You can't have all any number for L values. Always L will be restricted by this rule. Restricted by the selection rule. Okay. What values can be selected for L? What values can be selected for L when you are with the first energy level? When you are with the first energy level, what values can be selected for L? So it is, those values are starting from 0 to n minus 1. If the n is 1, 1 minus 1 is 0. 1 minus 1 is 0. If the n is 1, 1 minus 1 is 0. So 0 to 0, all the integers. 0 to 0, all the integers, they are just 0. So only the 0 is available as L values when you are dealing with the first energy level, n equals 1. Let's think about this one. When the n is equal to 2, let's see what values are available. When the n is equal to 0 to n minus 1. N is 2, n minus 1 is 2 minus 1, that is 1. So 0 to 1, all the integers are available as L values when you are dealing with second energy level. 0 to 1, the two integers are available. So 0 and 1 only, those are available. When it comes to n equals 3, the third energy level, what are the L values available then? 0 to, the n is 3 now. 3 minus 1 means 2. 0 to 2, the integers. So 0 till you come into 2, 1 and 2. Till you find the 2, the integers. Those are the L values available. When it comes to n equals 4, the L values available is actually 0 to 4 minus 1. 4 minus 1 means 3. 4 minus 1 is 3. So 0 to 3, the integer values. 0, 1, 2, 3. Those are the values available. That means, what are the orbitals then possible? Orbitals possible. Those are actually, I can write like here, even here. The orbitals possible is, so these are the two, one is at the first energy level, L value is 0 means S. At the second energy level, L value 0 means S, that means 2S. And second energy level, L value 1 is P, 2S, 2P. Here, third energy level, L value 0 is S, third energy level S orbital. Third energy level, P, L value 1 is P, 3P. Third energy level, L value 2 means D, 3D. See? Fourth energy level, L value 0 is S. L value 0 means S subshell. L value 1 is P subshell. L value 2 is D subshell. L value 3 is F subshell. Third energy level is F subshell. Sorry. Yeah, no? So it's fourth energy level is F subshell. So those are the available subshells with corresponding intervals, right? So you can complete this table, right? Now just complete this one to wind up. Actually, this is what mentioned at the next page, like this. So you can clearly see at the next page, no, the n values, the energy increases. You have that diagram in your picture, next page. No need to draw this one. No need to worrying about drawing this one. The L values will be appear like this. Right, no? So that is the idea. So just complete this one, Lamai. I'll send you a picture of this one as well, right? So, okay, no? So do you have any question regarding this one, Lamai? So if not, we can wind up at this stage. Are you clear? So I'll send you a picture of this one, Lamai. No worries about that thing. Or you can have a screen capture as well. So L values are restricted, right? L values are decided according to n value you are dealing with. According to n value you are dealing with, the L value will be decided. 0 to n minus 1, those are the available values with L. Right now? Okay then this is there, right? This is there at your book at the next page. No worries about that, drawing that thing. So right now, then we'll wind up at this stage, right? And we'll start next day's discussion from here, and we will continue the discussion about the ML value and the MS values as well, the magnetic contact number and the spin contact number, and we'll go forward, right, from there. Okay, so that is all for today. I think you are not with much of questions today, right? So if you have any questions, you can just send me to send those things to my phone number. You know that thing, right? This is my phone number, right? One day I also mentioned. So this is my number. So you can send any question to here, right? Rukshanshu, right? So then let's wind up at this stage, right now. Then goodbye. See you next week. Good night.